TUBR. Welcome everyone to the second part of the device control. Let me see. Our first presenter was not joining us quite yet. So I would like to offer Sonia Warchik to go first, if you could, Sonia.
Yes, sure. I can go first. Thank you very much. Okay, let me just start sharing my screen, and I'm ready. Okay.
Okay, we hear you very well.
Excellent.
And we now see your whole desktop.
Okay.
Okay,
now
and now present review.
Okay, thank you. Excellent. Well, thank you very much. Good afternoon, good evening, everyone. My name is Sonja Vrcic, and I am Control System Architect at the SKA Observatory. So I will provide a brief overview of the SKA Observatory for those who haven't heard about our fantastic new facilities and being built, of course, and then talk about telescope control systems, what do we actually have to monitor and control, requirements, challenges, and more specifically design patterns for implementation. So SKA, oops, just go out of it. So SKA Observatory comprises 2 radio telescopes and spans 3 continents. The telescopes are located in Australia and South Africa, and the headquarters is located in the UK. The blue here shows the member countries that are contributing to development of the telescopes. The design for the telescope was developed during the pre-construction. We have successfully completed the critical design review, and on the 1st of July this year, the construction of the telescopes officially started. So it's a very exciting time for us. The contracts are being awarded, and our team is growing. So if anyone is interested to contribute to this great project, please check our website. Oops, pardon me, I just skipped a slide that's related to science goals due to limited time, but you can check our website for that. But I will only say that the name square kilometer array comes from the goal to build a radio telescope with a collecting area of 1 square kilometer. And the science motivations to do that are explained on our website. But instead of building a single gigantic dish, radio astronomers often use the technique called interferometry. And so the signal collected from multiple receivers is superimposed to cause the phenomenon called interference. And then, that is used to extract useful information for the target sources and eliminate anything else that's considered to be just interference. So once again, the low frequency array telescope, that's one of the 2, is located in Western Australia. Its observing range is 50 to 350 megahertz, and it consists of more than 1,300 log periodic antennas that look something like this, like a Christmas trees, and are high about 2 meters, and of course, pointing to the sky above us. The mid telescope is located in South Africa, in Karoo region. It's observing in the range 350 megahertz to 15 gigahertz, and will consist of close to 200 dishes, 15 meter in diameter. Offset Gregorian dishes look more or less like this. So this is an overview of the radio telescope for those who are not familiar with the design, of course. Here I list the functions that that are required. What do we need to implement, and provide some overview of the technology so that it is better understood what actually we have to monitor and control in the telescope. So the receptors collect electromagnetic waves, the signal is digitized, timestamped, data samples are then sent for further processing. It's still real-time processing, and the techniques are correlation and beamforming. The results of that, again, packetized and sent for further processing, which is usually near real-time processing this time. Let's say pulsars, searching for pulsars, or precisely timing known pulsars, calibration of the telescopes, creating data sets, and then data sets are stored, and further batch processing occurs where actually the radio astronomers create images to show that invisible sky, so to speak. So the techniques that are used in the radio telescope, in mid, where we have dishes that needs to be moved, we have servo motors, so we have to control those, and of course analog hardware exists in both cases, because the signal is collected but then digitized, and so we have PLCs, FPGAs, CPUs, and then further digital processing again. We use both custom and COTS hardware, FPGAs, CPUs, GPUs, all real-time processing is basically done in the FPGAs. And the data processing, batch processing, is performed on high-performance computing platforms. So that would be the overview. This does not show the infrastructure, which consists of the facilities, roads, landing strips, because the telescopes are located far away in the deserts, power, water supply, networks, masers, IT equipment, and so on. And of course, the large data archives for the scientific data, astronomical data, engineering data, and so on. So this would be the range of equipment that we need to monitor and control. I'll concentrate mostly on the radio telescope. We will have a communication and will be collecting some information from infrastructure, but that will be limited, and I'll explain how we do that. This is a high-level view of software in the observatory, where these blue components, they depict and represent the signal chain, where signal is collected and then forwarded for processing, and this processing occurs mostly in digital hardware and then high performance platforms, while the green represent the control system. We have telescope monitoring control for the overall telescope, and then each of the subsystems, of course, includes their own local monitoring control. And although I here on the picture show this as a thin layer of the monitoring control software in green, I think the reality actually strikes me that it's more like a nervous system in a human being or other animals, whereby tentacles of the control system go all the way down for each and every component where it is that we need to monitor and control. And these are huge systems that consist of hundreds, literally sometimes thousands of units of the boards with the FPGAs and CPUs and GPUs to process that amount of data, because in the mid telescope the instantaneous bandwidth is 5 gigahertz of data coming from each receiver. So what are our requirements? What do we actually need to do? So the functionality can be divided in two groups, monitoring control of equipment and the monitoring control of the observations, or in other facilities, scientific facilities, the term experiment would be probably used. So for the equipment, we have a standard set of requirements to provide monitoring of equipment, report status, faults and errors, archiving, periodically archive selected monitor points, provide an API to trigger state and mode changes, support hardware, firmware updates, support testing and debugging, and also we need to do that at all levels, at the level of the telescope, but also for the subsystems and individual components. To support observing, we have to be able to configure a telescope for desired observing mode. Each telescope supports several observing modes, and many parameters may be modified. We also have to point the receptors and beams that are synthetically formed in low and track the sources and provide regular updates during the observation to track the source. of course, start and stop the data processing, save the data products, and most interestingly, because of the size of the number of antennas and receptors in each telescope, to most efficiently use the telescope, there is also a requirement to be able to subdivide the array and operate each subarray independently. So a number of receivers is assigned to a subarray, and that subarray can be operated independently from the others. And finally, of course, but very important are the non-functional requirements. And I here just wanted to emphasize what I find it's most important, and that's resilience of the control system, because it must be able to function in the presence of errors and faults. Reliability should never, literally never fail. And of course, performance is important so that the commands and requests are executed in a timely manner. So how do we implement it, our controls implement our system to support this? And so I will just, provide a brief overview. First of all, in an interferometer, and both our telescopes are interferometers, the functional view does not always directly map to the physical view, to the equipment. One component may be used by all of the subarrays and still have to be, shared seamlessly. And so this requirement to operate each subarray as independent telescope further complicates this mapping of the functionality to the physical equipment. And therefore, control system provides two views, provides a physical view, shows the status of equipment, individual components, subsystems, but also the functional view, where we show, subarray and its overall status and how it is configured and what it's doing. We also use hierarchical approach and apply it in both physical and the functional view, so that these large systems are organized hierarchically, and at each level we provide the monitor and control and provide engineering interfaces. And control logic is implemented within subsystems and components. So we push intelligence down close to the components, and this distribution of control logic supports loose coupling of components, which in turn supports the resilience of the system. So these are some of the design patterns that we've basically decided and determined a common API that we provide. So each subsystem implements the master controller, which is a single point of access to provide the overall status. And of course, the physical devices are modeled, and we can display there each status, but the master controller monitors all that. The subarrays, we support 16 instances. Then they monitor the resources and capabilities. This would be like a logical devices that we have. And of course, also we defined a standard set of state and mode indicators to wherever they apply. We very early in the design phase made the decision to use Tango controls as the base for implementation of the telescope control system. And Tango controls, we just heard in the previous session, they also used is an open source device-oriented toolkit for controlling any kind of software and hardware, can be used in SCADA and distributed control systems. The key concepts are the Tango device, which is basically a software component, an instantiation of a Tango device class, which models a component or a system it uses, and then the Tango device server, which is the execution environment for it. So this would be a very simplified view of the control software, just to illustrate how we replicate this design pattern again and again and reuse it, and also provide some hierarchy. Hierarchy goes way deeper because our systems are complex and consist of hundreds of components, so we have to organize them. So
we have about 2 minutes left.
Okay, I think that's enough. I just have, two points to make. And one is that, when using Tango, we decoupled Tango API from the system logic. So that basically the Tango device provides API. Yeah, that it provides a thin layer, of API, while a non-Tango class called component manager implements the system logic. And we do that so that we are more independent from a framework. That was our motivation. And finally, we want our control system to use loose coupling of components. So if one component fails, that it does not trigger other failures. And to support that, we use asynchronous communications. We implement input queue as appropriate where needed. And also we use JSON to pass configuration messages, and which in turn, supports weak typing and proper modeling of the configuration. So this is an overview, or just a summary of the design patterns and my last slide. So basically what we do, we have a hierarchical organization of the control system, distributed control of process logic. We decouple physical and functional view, use a set of SKA base classes to provide standard API, use Tango control framework. We decouple Tango API from the system logic. We use JSON to pass configuration messages, and we use asynchronous communications. So this would be on, so thank you very much, and I'm willing to take any questions.
Yes. If anyone would like to pose a question into a QA here, or just raise your hand. Let's see. Well, I could ask a question. It's clearly in your design of the system, resilience and loose coupling was important. How often practically communications break between the components? Is it something real, or it's like worst case never happens?
How often it fails? Well, the system, as I said, will consist of really literally hundreds and thousands of anyway. So when we did the analysis, the FAMICA and so on, it will happen. Something will be failed virtually every day.
Oh, wow.
So there will be a server or a board or interface, and so that's why for us resilience, ability to function in presence of failures and recover from failures is extremely important.
Wow.
Plus, we also have our system is distributed between the desert and the processing facilities that are located literally thousands of kilometers away. And operator also will be hundreds of kilometers away.
Yeah, that's what I was wondering about. Okay, thank you very much. I think you got one more question in Q&A, so maybe you just answer it through online. And
okay,
thank you. Thank you again.
I will stop sharing, and thank you very much.
Thank you.
Thank you, Sonia. Next up, we have Ralph Lang, who's a control systems coordinator at ITER. The topic of his talk is nominal device support as a software framework for measurement systems in diagnostics. Ralph, we can see your slide nicely. Yeah, if you want to go for it.
Do you see the slide? Yeah, probably.
Yes. Yeah.
Good. So hello, everyone. I'm Ralph Lange, working for the ITER Controls Division. And today I'm talking about how we are using nominal device support, NDS version 3, to build a framework for the INC of ITER diagnostics. And so what is driving this development? It's this. ITER will use more than 55 diagnostic systems. Most of them are unique, complex, highly specialized. Scale is the big challenge in ITER controls. To make it more fun, many of them are in-kind contributions. That means that we have about 20 or 25 design teams distributed all over the world that are designing those diagnostic systems, which will be delivered to the plant here in France. So to be able to manage this, standardization is our main key, and standardization of everything, of the design process, standardization of the hard and the software. And this project is about standardization on the driver integration level. I will first do a quick recap of the NDS basics and concepts. then show all the different pieces and parts that we added to create our framework on top of that. Have a quick view of on the latest developments and draw the conclusions at the end. So the NDS basics. NDS was initially developed by COSY-Lab. We had a talk yesterday about one of their own NDS-based developments. For this diagnostics framework, we have partnered with the Technical University of Madrid, Mariano Ruz, and GMV Aerospace as contractors. NDS breaks a system down to small functional blocks that they call nodes that are then instantiated in a hierarchy to build a device. Obviously, the hope is that for these small blocks that they are easier to reuse and easier to test. Easier testing will also be helpful for maintaining a high software quality standard. For ITER, many of the diagnostic systems are contributing data to the plasma control system, so the quality requirements are pretty strict for that. For all of that, you have to keep in mind that we are not developing the systems. We are just providing the framework that we hope everyone else is using to design the systems with. So comprehensive and complete user and developer documentation is also a key, so that these designs will really be the way that we expect them to be. Last not least, the diagnostic systems, we want them to be able to run using EPICS and using eventually the real-time framework that our plasma control system uses. Implementation-wise, NDS is not really exciting. It's a C++ library using pimple pattern. Device drivers are plugin libraries. A device driver, as I mentioned, is a structure, a tree-like structure of nodes, and every node allows access through its variables, which are called NDS PVs, and every node contains a state machine. The NDS core module, software module, is basically a collection of standard nodes, pretty much base classes, covering all the functionalities that we think the diagnostic will need. Data in, data out, basic I/O, timestamps, trigger generation, management of triggers and clocks, programming the backplane of these crates. That makes that the standard nodes have a well-defined set of variables and functionality that goes with it. So when you are adding a driver for a new device, you basically define your structure that your device have, or you draw the structure, and then you pick the standard nodes from the collection that you need, and you provide new implementations of these standard nodes for your specific device. This is basically how a new driver gets done. The upper level interface is called control system interface in NDS, and it's basically connecting the NDS device to the context that it's running in. For now, we are running NDS devices inside a text fixture for the testing, and we're running them inside EPICS IOCs for development. There is a plug by COSY-Lab to run them inside a Tango device server. As we are not using Tango, we have not tested that. And still on the to-do list, we want to be able to run the NDS device as part of the ITER real-time framework node. The idea is that when you're developing an NDS system, you're running it in the EPICS IOC. And when you have it working, you're taking the EPICS IOC that does all the configuration, control, and monitoring, and swap it out against the real-time framework that is then running the same NDS device with no changes in the code as part of the real-time framework. Coming to the different pieces that we developed during that in the last years, to support hardware from the ITER hardware catalog. That's another standardization thing. We have written drivers for the timing and triggering card, the multifunctional data acquisition boards. We are doing all the National Instruments PXIe here, and the FlexRio board that also does data acquisition, but with an FPGA and a data acquisition module on top of that FPGA. Outside of ITER, we know that Teledyne offers an NDS driver for the ADQ boards that has recently been enhanced to for using it at JET by the UK AEA. The second set of device drivers that developed is for the micro TCA form factor. These are the two form factors that we suggest for ITER diagnostics. And there we selected a similar set of boards. One is the timing and trigger generation board. The other one is a multifunctional data acquisition board, this time also based on an FPGA. And for outside ITER developments, in addition to the Teledyne board that I mentioned, the ESS has developed drivers for two boards. One is one of their Yoxos boards, and the other one is a stroke digitizer board. The second set of pieces that we developed, we called NDS plugins. A plugin is smaller than a device driver, and it's mainly used for communication. So we have the NDS SDN plugin that is our publisher for the real-time communication network. That's one way that a diagnostic systems can push data to the plasma control system in the end, is to publish it on the SDN network. We have developed a plugin for DAN, which is our high bandwidth scientific data archiving system. And we have developed a plugin for PVXS. The idea is that this will be used to integrate commercial and slow devices that have an existing EPICS integration. It's a NES plugin that is a PVXS client, so it can connect to anything on the outside that is integrated in EPICS. The NDS system is the next thing that we developed, and this is basically the device driver for the device that bundles other devices into a complex system. The idea is that everything that is specific to your application, to your measurement, should add up in the NDS system, which manages and controls all the underlying devices through the device's variables and by doing hierarchical state machines. Another thing that the NDS system can do is it can limit the number of variables that are exposed to the control system, so that focusing on those variables that are really important for this measurement that you are creating with that NDS system. To support our users or developers better, we created an NDS system sample application that takes like one of each of our module drivers, puts them all together in one complex system to show how we envision these complex systems to be combined from the device drivers. And the view into the next generation of FPGA systems. This is a UPM in-house development. They did what they call the iRio OpenCL driver. This is taking the current communication with FPGAs that we have that is completely based on the National Instruments toolchain with their Linux driver for the Rio architecture and LabVIEW FPGA on the other side, and moves that towards the Intel FPGA and OpenCL stacks. This immediately opens up the possible targets, and we have currently, or they have currently, two target platforms supported. One is directly to an FPGA from an Intel host using Intel FPGA and OpenCL, and the other one is to a system on a chip device, which in addition uses the Xilinx Vitis environment, and which is basically the firmware that is running on the system on the chip. That is interesting because it will allow eventually to connect high-end devices that have been developed by industry for the self-driving vehicle market. And at the same time, while we are able to connect to these really fast devices, it reduces the amount of code that we have to manage drastically, because all the communication and all the firmware on the systems is handled by the OpenCL stack. And with that, we hope that this will be one way that our users can focus on their application and only provide their application's code. So after 4 years of developing this, I would say this is in a pretty good shape. We have the drivers for all, not all, but for a good set of different boards from our hardware catalog for both the PXIe and the micro TCA form factor. We have the nodes that are necessary to do all the communication for the real-time stuff for archiving with EPICS IOCs. We have a sample application that shows how to do a complex system. We have a full set of documentation. We have tests for everything. And we see that, and this is really good news for us, of course, we see that NDS is also being used outside of ITER. So there's hope that other devices might get supported without us doing the drivers. So ending up with the credits, thanks to CozyLab, who did the initial NDS development, thanks to both the groups at UPM and GMV for their great work along the last 4 years. And thank you for your attention.
Thank you, Ralph. I wonder if we can take one very quick question. If there's none, then perhaps we should carry on in the interest of time. If you have any further questions, please select in the Q&A for any future questions. Thank you, Ralph. Over to you, Mike.
Okay, thank you, Ralph. Next, we have Najim Al-Saqib. Najim is a control systems engineer at LINAC, and he's talking control system for 6 megaelectron volts linear accelerator at LINAC project. Please go ahead, Najim. Okay, we see your slide. We don't hear you, so I need to unmute you.
Can you hear me?
Yes. Yes, go ahead.
Thank you. Thank you for the introduction. Well, my name is Najim Al-Saqib, and I am working as control system engineer at the LINAC project PINSTEC. The PINSTEC is the premier R&D institute of Pakistan, and it hosts the Pakistan first research reactor, and LINAC project is part of it. So I'll present the control system status for the 6 MeV linear accelerator prototypes that are currently being developed at the project. So let's have a brief introduction about the project. The objective of the project was to develop the indigenous RF linear accelerators ranging in the energy of 6 to 20 MeV for medical and industrial applications. Because of the expensive Linux that are being imported for the medical centers and various industrial applications. The phase 1 of the project was mostly in the R&D section, and now in the phase 2 we have developed the prototypes of the industrial non-destructive testing application, and other future applications are also in process. And the groups in the project are according to the subsystems that are consisted of the linear accelerator, and the accelerator controls and electronics group, which I'm part of, is responsible for developing the electronics and control system, as well as the IT infrastructure for the control system network, and also to the office network for providing services to scientists and engineers working at the project. So these are the 2 LINAC prototypes that are currently being developed. The left one is the medical prototype, which is under process, and right one is the industrial. Both are 6 MeV, and the industrial and non-destructive testing linear accelerator is in the last stages, and the experiments are being done and results are satisfactory. So this is the block diagram of our linear accelerators, which consist of the main components. The difference between these linear accelerators is that the medical linear accelerator is glycron based, and the industrial non-destructive testing is magnetron based, and both of the accelerating structures cavities for the linear accelerators were designed at LINAC project. One was fabricated in the IHEP China, and one was based and fabricated in Pakistan. And we are having some difficulties regarding the vacuum sustainability because of less infrastructure, the mechanical infrastructure available. So I'll present the electronics and control interfacing with the major subsystems of the linear accelerators. First of all, let's have the control system architecture. It is a typical 3-layer architecture. The medical Linux consists of APEX as the middle layer, and instruments, controllers, and PLCs act as the front-end layer for the linear accelerator hardware, where various phenomena need to be monitored and controlled. And the graphical user interface, it consists of the Phoebus Control System Studio. And the industrial Linux was also based on this architecture, but as it is going to be a product, so we shifted it to the Siemens PLCs only. The middle layer consists of Siemens PLCs, and front-end layer consists of instruments and controllers. And the graphical user interface is developed in the Siemens WinCC RT advanced software. So first of all is the RF subsystem, which consists of the RF source, either the klystron or the magnetron, and the HV pulse modulator as the power source for these RF sources. For the medical Linux RF system, we have the K-series klystron modulator, which is interfaced with the APEX IOCs. APEX IOCs are all of the IOCs are soft IOCs in the CentOS 7 operating system. The klystron K-series modulator is controlled by the Ethernet interface over the Modbus TCP protocol provided by the vendor. And this Stanford Research System signal generator provides the signal for the klystron preamplifier, and the DNC digital delay generator acts as the external RF trigger for the system and also for the synchronization of the RF pulse and the electron gun pulse. And the forward and reflected powers are measured through the diode detectors, which are connected to the Roland-Schwarz oscilloscope, and this oscilloscope is interfaced via the APEX soft IOC. The graphical user interfaces are developed in Phoebus Control System Studio. Previously, all the interfaces were in the Eclipse-based control CSS, but later on we shifted to the Phoebus Control System Studio, and we are happy with that. And the industrial Linux RF system consists of the indigenously developed 48 kV 110 amperes pulse modulator. It is controlled through the Siemens S7-1200 PLCs, and the magnetron electromagnet power supply is controlled via the S7-1200 communication module, and it controls over the serial interfaces with RS-422 protocol. Next is the electron gun filament system. It consists of the TDK Lambda Zub series power supply, and for medical Linux, we have interfaced it via the APEX IOCs. And the serial interface is converted to the Ethernet interface, and we have done that wherever applicable because of the easiness and the reliability of the Ethernet network. And as the electron gun filament power supply is raised to the high voltage, and it's approximately 30 kV, so we have converted the Ethernet media via the media converters to the optical fiber, and then again to the Ethernet into the APEX IOCs. And for Siemens S7-1200, the converters of MOXA are used that directly convert the RS-422 protocol to the optical fiber, and then again to the RS-422 into the communication module of the Siemens S7-1200. So next is the vacuum system. Vacuum system consists of the Agilent Technologies vacuum gauge controllers XGS600, and these are controls in the same fashion as the previously described. The MOXA, a serial device server, converts the RS-232 to the Ethernet and then into the APEX IOCs. And for Siemens S7, for the industrial Linux, Siemens S7-300 is used to acquire the analog signal available in the vacuum gauge controller, and it is programmed in the TIA portal and then displays to the touch panel in the WinCC RT advanced software. Next, we have the cooling system for measuring the temperatures of the linear accelerator at various locations. The K-type thermocouples are used. They are converted into the current signal via the Phoenix temperature transducers, and then into the Siemens S7-300 PLCs, and then again to the Siemens S7-1200 and 300 PLCs are interfaced with the APEX IOCs through the S7 Nodave communication module, and all of the other devices, the commercial off-the-shelf equipment is mostly interface via the ASN and stream device support modules of the APEX. And this is the indigenously designed chiller, which controls the temperature of the system. And based on the readings from the thermocouple, we control this chiller to control the temperature of the cavities and other linear accelerator hardware. So there are 3 stepper motors that are currently deployed and mostly in the industrial Linux. First is the stepper motor for a magnetron frequency tuning. It is a manual process right now, but we are soon looking into the automatic frequency control of the magnetron. And next is the for the fine tuning of the power injection into the cavities. It is the E-tuner stepper motor. And then for the modulator output voltages, they are controlled via the 3-phase variac that is motorized. And that stepper motor is, these stepper motors are controlled via the technology objects that are available in the Siemens TIA portal. And this S7-1200 is then communicates with the touch panel through the WinCC advanced software. The Beauty archiver system is deployed for saving the history of the process variables. The archive engine command line tool is configured with the necessary process variables that need to be archived, and the MySQL community edition server acts as the relational database, and then Phoebus data browser is used by the operators to view the history of the process variables. Next, the alarm system is the Beast alarm system of the Control System Studio. The alarm server command line tool is configured, and the alarm panel, alarm tree, and annunciator are used by the operators to view the events, important events happening during the operation. These are a few of the operator interfaces that are developed in the Phoebus. And these are displayed on separate LED screens in the control room. And this is the these are the WinCC RT Advanced HMIs. They are displayed on a single operator console that will be used for operating the non-destructive testing linear accelerator. So the RF conditioning and electron gun filament conditioning, and also the daily operation of the RF power, which needs to be gradually increased from a low level to the high level, and the ramp up, ramp down of the electron gun filament voltage are automated using the EPIC sequencer module. I have a poster session today for this. And next, the IT infrastructure consists of the 2 networks that are isolated. One is the technical network consisting of the control system, and second is the office network. So I also have a poster session for this on Thursday. And next, the electron guns that are installed in the linear accelerators are indigenously developed by the electron beam and diagnostics group of the Linux project, and they are tested in a separate electron gun test facility. Its control system is also developed by a group, and I am having a poster session for this today. So that was the update of what is happening at our facility and what we are doing. This is at a very low level, but hopefully we'll get along with the control system upgrades and improve the system. So thank you for the this virtual conference that enabled me to participate, and also the literature that is available by the EPICS community and the this conference proceedings. It guides us to move in the right direction. So thank you, and any questions are welcome.
Yes, thank you, Najim. Thank you very much. So let's see if there's any questions. Please post them into Zoom Q&A or just raise your hand. Okay, well, it's almost perfect time to move to the next presentation. So please follow up with Najim. Thank you very much again. Please follow up through the conferencing tools. Back to you, Johan.
Thank you, Najim. Next up, we have He-Yan Wang, who's a control systems engineer at SSRF. The title of his talk is Control System of Cryo Module Test Platforms for Shine. So if you can just unmute your mic. Can you please share your screen?
Okay, can you hear me?
Yes.
Yeah, you're fine.
Good.
And we see your slides, so you can go ahead.
Yes. Hey, hello everyone. I'm He Yun Wang. Yeah, and today my topic is control system of cryo-module test facilities for Shine. This is my outline. Shine project introduced cryo-module test facilities control system. It includes temperature, pressure, cryogenic valve, liquid level, heater power, vacuum, functional safety, and IOC OPI AA. At last, we have conclusion. Shanghai High Repetition Rate XFEL and Extreme Light Facility is the first hard X-ray FEL facility in China. It builds a continuous wave superconducting LINAC with an energy of 8 giga-electron volts, 3 free electron laser angulator lines that produce 0.4 to 25 kilo-electron volts photon engine range, 3 beam lines, and 100 top volts ultra strong and ultra short laser system. Ultra high peak brightness and average brightness X-ray free electron laser pulse repetition frequency can reach 1 megahertz. Ultra fast pulse is less than 10 femtoseconds. We can see the accelerator from the top view. Here's the underground tunnel for Shine. A cryo-module workshop is built in the Shine Park. The infrastructure includes ultra-clean processing and ultra-clean assembly, precision mechanical assembly and testing, cryogenic component multifunctional test facility system, superconducting cavity vertical test facility system, and superconducting cavity horizontal test facility system. They are used for cryo-module assembly and functional testing. Shine has one set of cryogenic component multifunctional test facility, 2 sets of superconducting cavity vertical test facility, and 2 sets of superconducting cavity horizontal test facility. The cryogenic component multifunctional test facility is used to test the working life on the tunnel at cryogenic, the vacuum leakage rate and electrical performance at cryogenic of cold BPM, the working stability of superconducting magnetic and current lead at cryogenic, the thermal load of each temperature zone, and the vacuum leakage rate of the coupler at cryogenic. The superconducting cavity vertical test facility is used to test the performance of the superconducting cavity vertically to check whether the cavity has reached the design goal so that it can meet the needs of engineering. The superconducting cavity horizontal test facility is used to test the performance of the cryo module, check whether the cryo module meets the design goal, and make it meet the needs of engineering. The control system implements comprehensive control of all types of device in the test facilities of cryo module, and provides a facility for device debugging and operation to meet the needs of testers and engineers in terms of device monitoring and control, data acquisition, storage, and analysis, and so forth. The device control includes local control system, vacuum control, and power control of each test facility of the cryo module. The overall control integration contains control network, operating environment, data storage, user interface, and center control room. The control system has 4 design objectives. It has the monitoring and control function for facility pressure, temperature, liquid level, cryogenic valve, vacuum signal, superconducting power supply. It has the interlocking function with the cryogenic factory control system and the LLRF system. It has the monitoring and the control function for heater power supply. It has the data communication function with the cryogenic factory control system. The refresh rate of device parameter is not less than 2 Hertz, and the response time is less than 200 milliseconds. The critical signal response time in the slow interlocking site is less than 20 milliseconds. Horizontal test facility local control system, vertical test facility local control system, and multifunctional test facility local control system can monitor and control the pressure, temperature, liquid level, vacuum signal, and so on. They can adjust heater power according to the RF signal to stabilize the lid of the cryo module. They can adjust the JT valve opening according to stabilize the liquid helium level. They can manually or automatically control the cryogenic valve for different processes. They are functional safety systems, including the signal of cryogenic factory and LLRF. They can exchange data with cryogenic factory control system. The local control system of multifunctional test facility realizes the monitoring and control of temperature, pressure, liquid level, vacuum, cryogenic valves, and heaters of multifunctional test facility. And also, it has the functions of recording and storing process variables and reviewing the historical data. The local control system of vertical test facility realizes the monitoring and control of temperature, pressure, liquid level, vacuum, cryogenic valves, and heaters of the vertical test facility. And also it has the functions of recording and storing process variable and viewing historical data. The local control system of vertical test facility has two sides of independent vertical test facilities. The vertical test facility 1 and the vertical test facility 2. The local control system of horizontal test facility realizes the monitoring and control of temperature, pressure, liquid level, vacuum, cryogenic valves, and heater of the horizontal test facility. And also it has the functions of recording and storing process variables and viewing historical data. The local control system of horizontal test facility has two sides of independent level test facilities. The horizontal test facility 1 for testing prototype cryo modules and mass production cryo modules. The horizontal test facility 2 for testing mass production cryo modules. Temperature sensor is Lakeshore Thermos, and temperature meter is Lakeshore model. It is integrated into PLC control via Profit Bus. PLC module is Yokogawa, which can connect up to 121 Profit Bus slaves. It has high precision temperature measurement. It is compatible with various types of sensors. Pressure transmitter has 3 types applied to pressure monitor. They are Keller series. PLC module is Yokogawa analog input module. Level gauge is AMI 2K cap level prop. Liquid level gauge is AMI analog output. The PID algorithm is used to realize the closed loop control of the 2K liquid helium level. There are 2 control methods, manual control and PID control. And the heater is Omega, which is used for cryo module heating up and cryo module compensation of total thermal load power. Heater power supplies model is TDK. The heater power supply has 2 modes, constant voltage and constant current. And constant current mode is used in this product. PLC includes Yokogawa DC digital input, relay digital output module, analog input module, and analog output module. It realizes switching on or off power supply remotely. Power failure status readback and power operation mode readback. It realizes the power supply output current value readback, power supply output voltage value readback, and power supply output power volume readback. 3 superconducting quadrupole ion power supplies are monitored, including power switch control, power load current monitoring, power reference current setting, power current slope control, power status monitoring, and so on. Interlock control is known as the machine production system as well. An interlocking production logic is established between the system and the device. When a fault occurs, it can reliably and quickly protect the important device of the accelerator, send an alarm signal, and report the fault information to the control system. For input signals, the system can realize the alarm latch reside and bypass processing from the software. Latch refers to saving the signal alarm state. Reside refers to releasing the alarm latch. Bypass means that the software temporarily releases the interlock response to the input signal. Device control is the core and cornerstone of the entire control system. MOXA 682B is stable and reliable IOC controller with efficient device control dedicated network. The runtime environment of the entire control system is based on CentOS 7, ICALEPCS version 3, and PYDM. PYDM is developed based on Python, the current mainstream programming language. Sorry, this is a conclusion. Device control is the core and cornerstone of the entire control system. And MOXA 682B is a stable and reliable IOC controller with efficient device control dedicated network. The runtime environment of the entire control system is based on CentOS 7. Oh, sorry, I've already repeated. I wanted to say Python, the current mainstream programming language, the superiority of PYDM are convenient sharing, simple configuration, and efficient running. Channel data storage prototype is based on Archive appliance. It has deployment of draw server system Archive engine. Thank you all. Thanks for your attention.
Thank you, Jan. Interesting talk. Are there any questions from attendees?
I think there's one question posted, Johan, in Q&A.
Could I know if the cryogenic interlock system is integrated into Shine's interlock system? As I notice, all the network in cryogenic control system is separated and you need a gateway to access it.
Way to access? Okay. To be honest, we have the gateway and firewall. This is just for Shine module test, not for the facility, I suppose. Yeah.
Thank you. I also have a question. The safety system network, is that separate from the control system network, or are they shared?
The network is separate from control system. Yeah, the network is, to be frank, I go back to the page for the network. Functional safety component facility. So separate control, because we, to separate the network. So each part, they will have the particular operation for the teenagers. So device control and mass network is the paramount device for us to study. Yeah.
Okay. All right, if there's no further questions. Okay, if there's any more questions, please use the Q&A chat. Mike, I think we can turn on to the next person.
Okay. Thank you very much again. And our next speaker is Sebastian Marsching. Sebastian is a managing partner at Aquinos, and he'll be speaking about integrating OPC UA devices into EPEX.
Thank you for the introduction.
Mm-hmm.
So
we see your slides. Thank you very much.
thank you. So today I want to present some works that Aquinos did for and in collaboration with Karlsruhe Institute of Technology, and specifically for use at the accelerator facilities at KIT. So my talk is split into 3 parts. First, I want to give you a very quick introduction into OPC UA, just in case you haven't heard of it yet and are not aware about what it is. Then I'm going to show you the Open 62541 library, which is an open source implementation of the OPC UA standard. And finally, I'm going to talk about the EPICS integrations that we developed. So OPC UA is a vendor-independent protocol for control system communication. It's designed to work in various contexts. For example, it can interconnect different SCADA systems. It can be used to integrate devices into SCADA systems, and it can, at least in theory, also be used for direct device-to-device communication. It's managed by the OPC Foundation, and it's a successor, but on a technical level not related to the original OPC standard. So the original OPC standard was, for example, limited to the Windows platform and used proprietary Microsoft APIs. And the newer OPC UA is completely independent and is really defined on the network layer using standard TCP/IP connections. It's supported by many different vendors, which include SCADA systems, programmable logic controllers, but also hardware gateways. So for example, you can buy a gateway where on one side you connect a Modbus or Profibus or something like this, and on the other side you connect it to an Ethernet network, and then you can access your traditional devices using OPC UA. So this makes it quite versatile, this protocol. It includes an information model and various subsystems, but I should mention here that most devices and software components only implement certain parts of the standard, because the OPC UA standard is just so vast that it doesn't make sense to implement everything for a specific device, because simply you won't need all of it. So usually it's only those parts that are really interesting in the context where devices used that are implemented. The OPC UA standard uses a client-server architecture. So you have clients that connect to servers, which again can be SCADA systems, hardware devices, things like that. It has an optional cryptography support, which means that optionally you can decide that you want to sign the communication between a client and the server. So in this case, you know that even if someone intercepts this communication, it will not be manipulated. You can be sure that if you're talking to a server, it is really this server and it's not someone impersonating the server. And of course, the same applies to the client. So you can be sure that the client is authorized to actually access the server. And you can also enable encryption if you need to. So if you have a network where you say, okay, I think there might be some kind of eavesdropping and this is critical data, I don't want this to be possible, then you can also enable encryption. Of course, in typical automation environments where we use secure networks, that's not really necessary. And I'd say that this protocol and this standard is really designed for Industry 4.0 or IoT applications. So that's what I mentioned earlier, where you also have device-to-device communication. And of course, this information model comes very handy, because it's a good way to discover which attributes, which functions a certain device actually offers. So Open 62541 is a library that is an open source implementation of OPC UA. It's licensed under the Mozilla Public License version 2. It's named after IEC 62541, which is the official standard representing OPC UA, and it's maintained by a group of German universities, research institutes, and private companies. So, for example, University of Dresden is one of the major partners in this, and I think also SAP, the large software company, for example. It's entirely written in C, and it supports Linux, macOS, Windows, and various embedded systems as platforms. So you can use it nearly everywhere. It has cryptography support if you compile it with Embed TLS. So if you don't want this dependency, for example, because you want to run it on a rather small microcontroller, you can say, okay, I compile it without cryptography support. But if you want to, then you compile it with Embed TLS and you have full cryptography support. It can be used in a single or multi-threaded way. It can act as a client or as a server. So you have a lot of options with this library and can adapt it for nearly any context where you might want to use it. So let's talk about the EPICS integration. First, I maybe should mention the EPICS integration that we did for OPC UA is not the first one. When we started this work, there already existed an EPICS integration for OPC UA, I think originally written by Ralf Lange from ITER. And the problem with this implementation was that it's based on a commercial SDK. You could download source code for the integration, but as the SDK was commercial, then you would also have to buy a license for this SDK so that you could get the source code for the SDK. And we really wanted a complete open source based solution. Maybe wouldn't have any proprietary components in. So we decided to write our own EPICS integration based on this library that I just mentioned. This EPICS integration acts as a client in the OPC UA world, and it connects to servers that provides their process variables and uses this to then have these process variables in EPICS. The EPICS device support supports all of the basic data types of OPC UA, and of course also arrays of these data types. We decided to embed the library into the EPICS device support, so you won't have to also download the Open62541 library, compile that, and make sure that everything works with each other. No, the source code of the library is really part of the EPICS device support, so you just download the EPICS device support, compile it. Of course, you will need EPIC space to compile it. And if you want to also enable the cryptography support, you will also need this Embed TLS library, but that's available on nearly every Linux system. I mean, you just install the package and then you can use it. We primarily use it for SCADA integration. So to integrate data from other SCADA systems into EPICS, but it should also work for other purposes. And in fact, we want to use it to also integrate PLCs into EPICS in the future. So let's have a quick look at how you use this device support. So in your EPICS IOC startup file, you first define the connection to the OPC UA server. So you need a connection handle, which you can freely choose. In this example, it's C0 for the first connection. Then, of course, you also have to specify the URL where the OPC UA server can be reached. And if the OPC UA server needs authentication, then you can also specify a username and a password. If you wanted to use cryptography, like signing or encryption, then this command would look slightly different, because then you'd also need to specify the path to the certificates which are used to back this cryptography. I omitted this in this example to not make it look more complicated than it really is. Of course, in the documentation, you can find the details on how to use cryptography support. Next, we define a publishing interval for the subscription. So in OPC UA, you typically have groups of process variables that you want to where you want to receive updates at a certain interval, and that's what we configure here. So we say, okay, we have a group called default, which is simply the group which will be used if you don't explicitly specify a different group in your EPICS record for the PV. And we set a publication interval of 100 milliseconds here. So this means that the OPC UA server will check at a rate of 10 Hertz whether one of the subscribed process variables has changed. And if it has changed, then it will send an update to the client, so to the EPICS IOC for that. Okay, so next, after we have defined the startup configuration, we want to connect to a certain process variable provided by the OPC UA server. And in order to do this, we first need to find out the identifier or so-called node ID of this process variable. And the tool UA Expert, which is provided for free by Unified Automation, is very handy for this. You can download it from the Unified Automation website. It's not open source, but as I said, it's provided for free. You can download it for either Linux or Windows. And if you connect to your OPC UA servers there, you can then explore the process variable hierarchy if you want, and look which process variables are provided by this OPC UA server, and then look at the details. And if you look at the details, you will then see the node ID, and also the namespace ID. So in this example, the process variable is defined in namespace 2, and the node ID is of type string, and the node ID itself is demo.dynamic.scalar.double. So that's what we'll need in the next step. By the way, this is what's nice about this information model provided by OPC UA, that you can really explore the process variables provided by a certain server and don't need some kind of documentation where, like, for example, in Modbus or something like this, where you have cryptic address tables where you have to look up things. So in the APEX record, we now can connect to this process variable. Of course, we have to set the device type, which is open62541 for this device support. And we have to define the input link. So here we reference this connection C0 that we defined earlier in the startup file. And next we specify the node ID. So we have a node ID of type string, which is defined by the prefix str. We have a namespace ID2 and then the actual node ID. In fact, in OPC UA, there are different kinds of node ID. That's why we need this str prefix. For example, UIDs can also be used as node IDs. But most servers that I have seen so far actually use the string type node IDs. And we set the scan field to IO interrupt, and this will have the effect that the subscription groups are used instead of polling process variables individually. So we could also set something like scan 1 second, but then this one process variable would be polled individually. And that's, if you have many process variables, that's much less efficient than polling them as a group. And for an output record, it's really the same. You just define it in the output link, and then you can write to this process variable. Nothing special to see here. Okay, let me summarize. The OPC UA protocol is an IP-based protocol for communication between automation systems, and it's supported by many different vendors. The open62541 library provides a free implementation of this protocol, and it's suitable for use on both PCs and embedded systems. Using this library, we created an APEX device support that enables the integration of process variables from OPC UA servers into APEX IOCs. And if you want to learn more about this project, you can go to our GitHub website, where you can find the source code, where you can also find the documentation, of course. And if you have any questions, you can ask them now, of course, but you can also contact me later by sending me a message or something, and then we'll figure something out. Thank you very much for the attention.
Okay, thank you very much, Sebastian. And yes, please post your questions or just raise your hand. Let's see here. I don't see any questions yet, but question, Sebastian, you mentioned that it's developed by a consortium of universities, but of course, you have this Aquinos. Can you tell us, in 2 words, what Aquinos is? What is the company doing?
Yeah, sure. So we are a company which specializes in software development and also consulting for large physics projects, in particular for accelerator facilities. And that's basically how we came into this project, because KIT wanted to use this already existing library. for the EPICS integration, but of course someone had to actually implement the EPICS integration to make the links basically between this library and EPICS. Yeah, and that's what we did.
Okay, and we have one person raise a hand. Let me allow him to talk. Martin Kieringberg.
Yes, hello. From Aquenos, there is also the EPICS device support for Camera TK, and Camera TK also has an Open 62541 based OPC UA backend. Would this has been an option to use this combination to get an EPICS integration into OPC UA?
Yes, I think it might have been another option. Actually, I'm not quite sure whether this backend already existed when we started this device support. I know what already existed was let's say, to do it the other way around for a Camera TK, that you could start an OPC UA server, which was providing stuff from Camera TK, but here we needed the opposite direction. So already existing OPC UA server and integrated into EPICS, and I'm pretty sure at this point in time this was not possible through Camera TK.
Ah, okay. And what is very interesting is this grouping of polling of polling multiple variables. This definitely is something where I'm not sure if it is available with the current backend.
Okay.
Okay. Thank you, Martin, and thank you very much, Sebastian, again. Very interesting talk. So on this, we are wrapping up our second session on the device control. Please attend our poster presenters, speed networking tables, but also our vendors and sponsors, right? You could also reach out to vendors. You know, they're helping with conducting these conferences every time, and they're waiting for, you know, to meet us. So please look around. There are many names you could recognize which are supporting control systems at large experimental physics facilities. Johan, do you have anything to add?
No.
Okay, well, thank you everyone, and I'll see you around.